now we're going to look at the procedure to use for calculating the V as a function of R graphs for finite charge distributions in general. Now, on our last page of notes, we saw the V versus R graph, right? So here we had the voltage versus R for the sphere. So we got that really from our point particle calculation, KQ on R. But we're going to see how to do this in general for any finite charge distribution, not just the point particle or the sphere. So let's go back. Well, we have a specific procedure to follow, and I have a summary of the procedure, kind of the rubric that you'll be used to be graded by when you do these problems, but it's also convenient to have on one page of notes the different steps that are taken to refresh your memory if you go back and look at these notes in the future. Well, we're going to be using the calculus version of the point particle voltage. The K dq on R is the calculus version of KQ on R for a point particle. So what we're going to do is we're going to take a look at all of these calculus point particle dq's, look at the voltage contribution dV they give to a point in space, sum them all up, and get our total voltage. Now, the first thing that you want to look for when doing this calculation is whether the R, the distance between the dq's, the charges that we're looking at, and the point in space remain the same. If R remains the same, then that comes out. Your integral of dq is q, and of course you will get the KQ on R that we're familiar with. Now, if the R is not constant, which it won't be in most cases, then you're going to have to replace the dq with our density equations. So we have the volume density. Now, again, the V's are tricky because we have voltage and volume, so the dq dV, right? If it helps, you can put a note in here to yourself that this dV is volume. So we get dq equals rho dV, we get dq equals rho dA, our area, or dq equals lambda dL. So this we're familiar with. Now, again, our V's are a little problematic, so both of these V's are volume, differential volumes. So we can get that in here. Differential volumes. We only have the two geometries, the sphere and the cylinder, and it's the same as we had for our Gaussian problems. The sphere is the shell, 4 pi r squared, that's surface area, times dr. The shell for the cylinder is 2 pi r times the length L, dr, gives us our differential volumes, and we will be using then the calculus version of V equals KQ on R, dV, actually, technically, we should have integral dV here equals K integral dQ on R. K will always be constant. If it's an area that we're looking at, please make sure you do get this into your notes. If it's an area we're looking at, we will be looking always with the polar coordinates where dA is ds times dr. So it's base times height. The base is the r d theta. So we have our dA equals r dr d theta. You do not have to ever prove that, but that might be one that is handy to memorize for this course and for the AP test. dA equals r dr d theta. So that's our basic procedure, and the case number 2 is so simplified that we're going to show that on this page of this lesson as well, this video. So here, if we have a ring of charge, so the ring of charge will be one of the easiest for us to consider. So the ring of charge is like a hula hoop. So say we have like this hula hoop, but a really thin one, with all of these dq's, these calculus point particles that go all around our ring of charge. So the voltage at any point in space from any one of the dq's, so the differential contribution from our differential charge is going to be K dq on R. But look, the R's all remain constant. So as we go around, all of these green R's have the same little r. The capital R is, of course, the radius of the hoop, so that when we integrate, that R is going to factor out. So let's get that in here. When we integrate, that r remains constant. It comes out of the integral along with the k. We're left with the integral of dq is q, and we integrate it from 0 to capital Q. We get capital Q. So our total voltage, dV, sums up from 0 to V to be the total voltage. So we get KQ on little r. If we wanted the voltage on the x-axis as a function of x, of course we would have to substitute in our little r, capital R squared plus x squared square root. So be careful about how the question is worded, but basically that is the procedure we would follow, and that of course is the easiest. Whenever r is constant, that will be the easiest, and we'll do the ones that are using those density substitutions on our following pages.